we started discussing the ingredients for the so-called balanced truncation of dynamical systems. Okay, and we were recalling the concepts of reachability and observability, and reachability and observability gramians in infinite time. Okay, they are very useful because they compute specific quantities which are relevant to us. First of all, the controllability gramian is also shown in your assignment, is related to the minimal amount of energy required, of input energy required to control a state from -infinity to 0, or reversely from 0 to infinity, but in backwards time. Okay, so we are talking about past input energy and future output energy, remembering that this is related to the Hankel operator and the Hankel matrix. Similarly, for the output, we are interested in the observability output of a specific state. Hence, we compute the observability energy of a specific state from 0 to infinity when the input is turned off. So this is future output energy. These two quantities, past input energy and future past input minimal energy and future output energy, without any minimization whatsoever, okay? These represent the main ingredients to assess the quality of a state. So if the input effort is small and the output energy is large, a state is very controllable and very observable. Then this is a relevant state for the dynamics. However, if the input energy, the minimum effort required to steer the state from 0 to infinity backwards in time, or from -infinity to 0, okay, if this is large and the output energy is small, then the state is not too controllable and not too observable. Hence, this dynamics is not so important for the main input-output mapping of the system. This is the way how things are going to be described from now on. Okay, and these are the main ingredients for the so-called balanced truncation procedure to approximate a dynamical system. Okay, we are also showing that the gramians P and Q have specific forms in the frequency domain. Okay, this is due to Parseval's theorem. This is a result from signal theory, okay, from signal processing, okay. Furthermore, the infinite gramians, they are the solutions of Lyapunov equations, okay. The first is the solution of the controllability Lyapunov equation, and the other one of the observability Lyapunov equation. Mind you that the system, okay, the system which needs to be approximated, this guy is stable and the system is controllable. Hence, P is positive definite and Q is also positive definite. Okay, and here it is. For those of you who asked about the Riccati equation, this is where the Riccati equation comes from P inverse. Okay, so the minimal effort or energy required to steer the state from 0 to infinity, and I would say here backwards, because this is in the past, backwards in time. Okay, backwards in time. Yeah. This is okay. This is the formula. This is the specific formula. Okay. Yeah, because this, I remind you, this is mean by U. Okay, U in L2. Okay, so finite energy input. Okay, and x0. Okay, and x minus infinity equals 0. Integral from 0 to infinity from U transpose du dt. Okay, all right. And since this has got this minimum, okay, this is the minimal. Applying, okay, apply optimization, apply optimization principles, okay, then you get the Riccati equation, and then equivalently the Lyapunov equation, okay? All right. We are not going to prove these things because they are not very necessary at this point, but you can find these derivations, you can find these notes anywhere in the field, okay? There you go. I've just seen the message of one of you.
Yeah, I just found sorry.
So you see, this is correct. This is good. Okay, fine. I don't mind. Use it. If you can use it, do it. Similarly, we've got the output energy. Okay, this has no minimal. However, there are versions where you can use LOW. You can use this. Okay, you can use this. All right, but these are different versions of the same problem. Okay, so essentially we look at the energy output, not at the maximal energy output. So these are the energy functions to be computed using the Gramians. Hence, the Gramians are really important, and not necessarily the Gramians, but their eigenvalues and singular values. Okay, so now we are just going to look at the procedure. Let's see, model order reduction based on balancing. This is what's to be studied. Okay, so what's the main idea behind this? The main idea behind is that we eliminate the states that are difficult to reach, okay, and difficult to observe. So LC, sorry, difficult to reach, LC, large in some sense, depends on what large means, and LO is small, okay? So this is when it's difficult to reach and difficult to observe. This is what means. Now, who is going to assess what large and small is? Okay, well, this is going to be assessed by sigma I, okay, which is the Hankel singular value associated with the state xi. Okay, this is the quantity that's going to give us. You already have this discussion in the previous chapters, but we just recall it. Okay, all right. So the above notions, they say here, they are basis dependent in the sense that we need to go to a specific basis. We need to change the coordinates. That's the idea of the basis, such that this is emphasized, because you cannot just see it. If you write a few differential equations, you cannot just assess this property only by looking at those equations. Okay, so you need to bring the system in a specific form. Okay, in a specific form, emphasizing these specific properties. Okay, so the idea is, they say, one would like to consider the basis where both concepts are equivalent, i.e. when the system is balanced. So essentially, you need to emphasize the same property, both of these guys, with one notion, in one shot. Okay, you need to catch two birds with one slingshot. Okay, this is what you have to do. Okay, so to do this, you need some quantities, some specific invariants, and we already know that these invariants are called the Hankel singular values of the system. Okay, first of all, how does the change of coordinates, or also called the change of basis? Okay, so this is change of coordinates. Change of coordinates. Okay, so how does this affect the Gramians? Okay, how does this affect the Gramians? So this is a change of coordinates, t. T is invertible, okay? This is what it says here. T is invertible. All right? Okay? So you just show now how the Gramians change, okay? Because e exponential of at times b, okay? You can write it as t eat t inverse tb, okay? Because this is the identity. This is the identity. So it's t e to the power at b, okay? And also b star e to the power a star t. This is b star e to the power a star t, t star. Hence the new reachability Gramian. So when you perform this change of coordinates, the reachability Gramian is changed like this. The new Gramian is T, P, T star. T, P, T star. Okay? This is one way to look at it, but you can also do it differently. Okay, so what's a change of coordinates? You start with x dot is ax plus bu, and y is cx. And then you apply the change of coordinates z. Z is tx. Okay, t invertible. Okay, hence x is t inverse z. Okay, then you apply the operator d to dt to this guy, and you remember that z dot, okay, doing this, we remember from the change of coordinates that z dot is t a t inverse z plus tb u, and y is c t inverse z, not x. Okay, this is a simple application of a change of coordinates. Okay, now this system has Gramians. This system has Gramians. Okay, so you have AW. Okay, not W. Yeah, W. Never mind. We call it W. Plus WA transposed plus B transposed. This is 0. And then you have these Gramians here. Okay, so you have T A T inverse. Okay, I don't know how to call this. The new Gramians, W bar plus W bar T A transposed, T transposed plus T transposed B, no, TB, sorry, plus TB B transposed T equals 0. Okay, all right, all right. So if you just, so the T here can go away and be T inverse. So you get, yeah, you multiply this with T inverse to the left. So you have A T inverse W, okay, plus double T inverse W bar T minus transposed A transpose T transpose plus B transpose T transpose equals 0. This is not C, but 0 equals 0. Now you multiply this with T transposed inverse. So T minus transposed. And you get what? Then you get A T inverse W T minus transposed plus T inverse W bar T minus transposed A transposed plus B transposed equal to 0. But this is this equation because they are identical. They are unique. So this is W. This is W. Okay. So W is T inverse W bar T minus transposed. Hence, W bar is T transposed W T. Okay? Or not? No, sorry, T, W, T transpose. T, W, T transpose. Okay? Look, this. Okay? So this is the effect of the coordinate transformation on the gramians of the systems. The same holds for the output. Okay? The only difference is that here you get the minus transposed and minus minus 1. Okay? These are called the counter gradient transformation of the gramians. Okay? So change of coordinates is it's exposing the gramians to counter gradient transformations. Okay, fine. But now, in order to bring the system, so what's balanced form? Okay, what's the balanced form? Balanced form means that we'd like W bar equal to M bar equal to sigma 1 diagonal to sigma n. Okay, where sigma I are the Hankel singular values of the system. This is, okay, so that means this coordinate transformation T, we'd like it to be a balancing transformation. This is what we want to achieve. So how do you build a coordinate transformation achieving this? Okay, so how do you build that coordinate transformation that achieves this property? Okay, how do you do that? This is called a balancing transformation, and we need to compute it. Okay, now here is an algorithm. Okay, and we're going to emphasize this, and then we're going to read a little bit in the book of Antulas about this. Okay, but the main algorithm, it's not the most efficient possible. There's numerous more efficient versions, but the basic algorithm to yield a balancing coordinate transformation is given by the following. So the balancing, we call it T-bal, just like MATLAB calls it. MATLAB is using this notation of T-bal. Okay, it can be computed as follows. First of all, you take the controllability gramian and you factorize it in Cholesky form. Okay, Cholesky form. Okay, what's a Cholesky factorization of a matrix? What is a Cholesky factorization? Okay, any matrix M is U transposed with U upper triangular. Okay, and this always exists. Always exists. This is always possible. Okay, Cholesky factorization. There is a MATLAB command called col. Okay, col. We can try to have a look. I don't have the MATLAB on this screen. I have it on a different screen. I'll just start the MATLAB and then we can see what all this means. Okay. So the Cholesky factorization, this is a main numerical method students learn in the first or second year. Okay. This is basic stuff. Cholesky factorization of a matrix. Okay, writing the matrix as the product of an upper triangular matrix. Okay, U transpose. Okay. Okay, fine. Now, you compute the eigenvalue decomposition of this matrix. Q is the observability gramian. So you multiply U star with Q and then with U, and you do an SVD, an eigenvalue decomposition of this matrix, okay, which is given by this form, okay, where sigma squared, this, okay, the sigma squared is exactly sigma 1 squared, sigma 2 squared, sigma n squared, and these are the Hankel singular values of the system. Okay, so this is a classic eigenvalue decomposition you perform on this matrix. Okay, all right, like diagonalization, for instance. Okay, you diagonalize this matrix. Okay, and the orders, why is it diagonal and not Jordan? Question. Why is it diagonal? Why is sigma diagonal and not Jordan? How are the Hankel singular values? Are they distinct or are they equal? How did we define Hankel singular values? Hmm? What do you think? How are these Hankel singular values usually? They are all positive, okay? And yeah, because we start with A, B controllable and CA observable. And not only positive, but also how? Hmm? When is a matrix diagonalizable? When can we diagonalize a matrix? When the eigenvalues of the matrix are what? You should know this from basic linear algebra. You ought to be familiarized with this. Do you know or you don't know? Hmm? When can a matrix be brought into diagonal form?
If all its eigenvalues are different from 0.
All what?
Eigen
Okay, eigenvalues should be non-zero. No, this is not necessarily. You can also have zero eigenvalues. No, but to have a matrix with only with the eigenvalues on the diagonal, but only the eigenvalues and not Jordan blocks. How should these eigenvalues be? One another, equal or different? That's the question.
I think different.
Different, of course, and that's why, because sigma 1 is sigma 2. This is why. Okay, sigma I plus 1, sigma n. That's why. And so this matrix can only be diagonal. So it can be diagonalized. Okay, that's why we can perform this simple transformation here and diagonalize this matrix, because we already know what's to be expected. Okay, and they're also ordered decreasingly. Okay, because the diagonalization algorithm can do that for you. Okay, and then you just compute the transformation. Okay, you just compute the transformation. This is the transformation. Okay, this is the transformation, and then it can easily be checked. Okay, so T-bal U T-bal transpose. I'm using transpose. They're using Hermitian because they can also consider complex values, but I'm restricting myself to real. This is the same. Yeah, okay. Okay, so this is sigma to the half, okay, because these are squared, okay, these are positive. Sigma to the half. So we can take the square root, okay. K star U inverse. This is not, should be P here. Sorry, not U. This is P. Okay, or W, whatever. Okay, P. T bell transposed. That's sigma. This is a diagonal matrix, so it's the same thing. K. This is no, this is U actually. It should be the other way, okay? So U minus transposed K sigma like this, okay? All right. Okay. All right. And this is equal to the other one with Q, to the other one with Q, okay? So, all right. T bell minus transposed. First of all, let's take it to the -1. So this is U, K star, K minus star, sigma -1/2 transposed. Q, not Q, not Q, not Q, not Q. Oh, yeah, Q. And then T bell inverse. So this is sigma like this. K inverse U transpose, okay? And these two, if you multiply them, you can easily recover PQ, or you can show that both are equal, they are both equal to sigma. Why is that? Because U star KU is this guy, okay? Oh, and P is U star, by the way. P is U star, okay? So this is P, okay? So P here, we just substitute it. So this is sigma 1/2 K star U inverse U star. This is P, okay? This is P because that's how we started it. U minus transposed K sigma 1/2. Now, this is identity. This is identity. So this is sigma half K star K sigma 1/2. But this is an orthogonal transformation for this here. Okay, for this guy, for the eigenvalue decomposition. So this is again identity. Okay, so this is just sigma. And the same holds for this guy. This guy is just sigma. So this is true. Indeed, this coordinate transformation is a balancing transformation because it's achieving this relationship. Okay, and sigma is the diagonal of the Hankel singular values. So, what is the input effort of state xi? State xi has LC xi, okay? It's xi times LC of xi, because LC now, because it's xi sigma of element I, xi. But this is sigma I, inverse, sorry. So this is sigma I inverse. So the effort to control is xi squared over sigma I. As we already know, we have already discussed about this. We discussed about this 2 chapters ago. Okay? And the observability, so the observability output of the same state is sigma I, sigma index I times I, because now the controllability and the observability gramians are equal and diagonals. They are both sigma in the balanced form times xi, but this is a different x. This is not the first x. Okay, this is in the new coordinates. Okay, so, or maybe I should say it differently. I shouldn't use x. I should use z. Okay. Zi, because we are in the coordinate z equals t bal x zi, and this should be also zi here, the zi squared. Okay, and the same applies here. So zi, so this is zi squared sigma I. Okay, now if sigma I is small, okay, that means controllability effort is large, and observability output is small. Okay, this is equivalent of saying that the state zi is almost non-minimal. This is almost non-minimal. Okay, if sigma I is large, then the controllability effort is small, which is good. We don't need much effort to steer the state, and the observability output is large. That means that zi is very minimal. Okay, is very minimal. This is of course under between quotes. Okay, so if you do approximation, okay, you have z1, z2, zi plus 1 up to zn. These are all the balanced states. How do you approximate the system? You only keep the first zi important coordinates, because from sigma 1 to sigma I, the Hankel singular values are relevant. Then the Hankel singular values are small, and so hence you can neglect that part. Okay. Okay. So sigma equals to diagonal of sigma 1 up to sigma n contains the n Hankel singular values of the system. Okay. There is also a variational interpretation. If you compute the balancing transformation, this is equivalent to minimizing all the functions of t, and you minimize this norm. This is a norm, okay? This trace here, this is a norm. You minimize this norm, okay? So this is an optimal transformation, okay, where this function takes this value, which is twice the sum of the Hankel singular values, okay? Twice the sum of Hankel singular values, okay? So how the balancing transformation T is the optimal solution of this optimization problem, okay? Please note that this is a quadratic non-convex optimization problem. This is very difficult to solve. Okay. All right. So what is balanced truncation in the end? Okay, where is the approximation we have been all talking about and looking for so long? Where is the transformation? Okay, so how do we perform the model reduction? Where is the approximation in all this? Okay, so the idea is that if you want to do balanced truncation, first of all, you need to compute the balancing transformation. Okay, how do you do that? So first of all, you need to apply the change of coordinates. You do W tilde is T bal W, transforming the given dynamical system into A tilde, B tilde, and C tilde. Okay, like this, applying a change of coordinates. Okay, then you look at the Hankel singular values and you realize that at index ni, okay, or k, okay, here they use k, okay, you realize that at index k, sigma k is much larger than sigma k plus 1. Then you cut at the index k and you partition the system into W tilde 1 and W tilde 2. Okay, performing this partition, so you have W tilde is AX, AW tilde, sorry. It's AW tilde plus B tilde U. Okay, this is equivalent. So you say W1, W2. So now you need to partition A tilde such that you get here W1, W2. And this is what? A11, A12, A21, A22. Okay, this is how you partition your system according to this specific specific ordering of the Hankel singular values. And you do this here. Okay, this is the partitioning of the system into blocks specific to the splitting into W1 and W2. Okay, the indices or the subscripts 1 and 2 denote the dimensions k, yeah, and n minus k, because this matrix, okay, this is a matrix in Rn, but this is partitioned now, and this has dimension k, and this is n minus k. Here is also n minus k, okay, and this is k and n minus k. So this is a good partition. This is properly done. Okay, this is a nice partition. You do this partition, okay. So the blocks with the subscript 1 correspond to the most observable and reachable states. Indeed, those are to the states W1. Okay, W1 contains W1 up to, or W11 up to WK1. These are the states. Okay, these are the states, and these are corresponding to the large Hankel singular values, sigma 1 up to sigma k, and W2. This is W12, W22, Wn minus k2. Okay, and these are corresponding to the Hankel singular value sigma k plus 1, sigma n, small. Okay, small. And these are going to be neglected. The blocks to correspond to the least observable and reachable states. We've been through that. So how do you take the first order? How do you take the reduction? You go back to this partition, and you neglect the dynamics. Okay, so this is equivalent to, these are dot here. Okay, so W1 dot, this is equal to A11 W1 plus A12 W2 plus B1 U, and W2 dot, this is A21 W1 plus A22 W2 plus B2 U. Okay, And how do you do this? You neglect these terms. You set W2 to 0. So this equation disappears completely. And the reduced order model is given only by this equation. This is called an approximation. This is called a balanced truncation of a given dynamical system. Okay, of dimension. It's an approximation of dimension k. All right. So the reduced order model of size k obtained through balanced truncation is then the system AR, BR, CR. Let's denote it like that, which is given by these blocks of dimension k. Okay. And the left and right, what are ROBs? Reduced order. I don't know what this is, but this is the coordinate transformation, you know? This is the coordinate transformation. You see? Now, this is one way to do it. Okay, this is one way to do it. You simply neglect this equation. You throw it away. Okay. Another way to do the things in balanced truncation is to only set or. Okay, so neglect. What we've done so far is called neglection. Neglect W2, setting it to 0. Okay. An alternative, they say with better results, because you also include the second part. Alternative is set not W2, but only W2 dot equal to 0. So then you get these equations. W1 dot is A11 W1 plus A212 W2 plus B1U, okay, plus B1U A12. And then here you get 0 equal to A21 W1 plus A22 W2 plus B2U. Okay? So what do you do in this case? In this case, you need to extract W2 from this matrix. So A22 W2 is minus A21 W1 minus B2U. And assuming that there is no zero eigenvalue here, assuming, yeah, you assume. But why haven't you got no zero eigenvalue here? Why don't you need to assume it? Why is it always possible to get A22 inverse? We made an assumption at the beginning of the procedure that A is how? The matrix A, the original matrix A is what? How's the original matrix A? What's the main assumption we do on the ABC to be able to do this procedure? How's the matrix A? How's the matrix A? Hmm? I'm listening. How's the matrix A to start with? Okay. A is stable, isn't it? This is equivalent that sigma to the fact that sigma A is in C minus. Okay, then any partition you make, okay, any partition in general leads to A22 invertible. Okay, because you cannot get a zero eigenvalue if you haven't got a zero eigenvalue from the very beginning. Okay, so this is generically this is invertible. Okay, so you can compute W2. W2 is A22 inverse A21 W1 minus A22 inverse B2U. And then you substitute this here. You substitute this here, okay? And your reduced order model is W1 dot is A11 W1 plus minus A12 A22 inverse A21 W1 minus so you can just set a common factor here, like this, minus or plus B1 minus minus A22 inverse B2 U. Okay, and Y is what's left of it. Okay, C1 W1 plus C2. Okay, and then you get this guy, A22 inverse, or minus actually, minus C2 A22 inverse A21 W1. And this is another balanced truncation reduced order model. Okay, this is the singular perturbation version. This is how it's called. Singular perturbation, singular perturbation. Let's call it variant, just like the virus. Now, okay. So you've got two variants of the balanced truncation model. Okay, two variants: the regular, the neglection one, the truncation one, and the singular perturbation one, where you recover some information also about the neglected part. Okay, you keep some information about that as well in your reduced order model, and you can compare in a later homework. You can compare these variants and see which one gives better results. Okay, now, of course, once you perform such an approximation, you need to analyze the error of the approximation. So you have to find a way to compute the approximation error of such modeling. Okay, so now you have two models. You have the TS original, and then you have T tilde or whatever, TRS from R from reduced. You have TRS reduced. Okay, so somehow you need to assess T minus TR. This is the error. This is the error, okay? Because what do you usually compare? Because you compare the output Y minus the output reduced. And this is somehow related to this difference. This is related to this difference. And how do you assess the error? You compute some norm. You compute this norm of this output, and you have to give it, this is like this, and you have to give it to some norm of the transfer function. There is a relation between these norms. The people from control studies have done these things in the second year when they were studying loop shaping with infinity norm and two norm and so on. Okay, so this is a signal norm. This is a signal norm. This is a signal norm, and this is a systemic induced norm. Systemic induced norm. Okay, so these are a bit different, but the idea is that you need to in order to achieve this, you need to study this guy. This is how we are going to do it. So we are going to do the error analysis, and we are going to use the Hardy H infinity norm. The H infinity norm associated with a system characterized by a transfer function like this. This is G infinity. This is the supremum by all the values of Z in the open right half plane of infinity norm of GZ. Okay, so this is the supremum from the maximal singular value of G of Z. This is the definition of the infinity norm. Okay, now we have some characterizations of the infinity norm of such a system. The infinity norm of a transfer function is the supremum over all frequencies omega in R of the modulus of the infinity norm of G of I omega. Okay, so this is omega, supremum of omega in R of this sigma max. Now, if you have one input, so for single input, single output, okay, we know we use this quantity and we do Bode plots. Yeah, we do Bode plots. Okay, where is, assuming this is the Bode plot of G, okay, so this is norm of G of J omega versus omega. Where is the maximum, where is the infinity norm of this guy on this plot? Where is it?
At the highest magnitude.
or maximum, okay?
Yeah, the
Here it
maximum.
is. This is very good. Here it is, okay? But this is only for single input, single output. For multiple input, multiple output, we need to use this quantity, okay? We need to use this quantity. However, what is the definition of such a norm? How is it actually characterized? This is the supremum after all L2 inputs of the energy of the output versus the energy of the input. You remember that Hankel singular values measure energies. It's all about the energies of the states. Hence, this definition falls into place, suits us to a T. It's very interesting. So this infinity norm is exactly what we need. We need to compare the output energy versus the input effort, okay? And this is the definition. This is the square root definition, okay? So this is very interesting. So that means that we need, when we look at the error, okay, we look at the error, we are looking this H infinity norm of the error T minus T reduced is the supremum by U of the energy of the error versus the input energy, okay? Where E here, ET, okay, is the approximation error signal, okay? So this is, we are going to apply this, to our error analysis. Okay, so the H infinity norm of the error system between the high dimensional and the reduced order models can and you will be used, they say here, as an error criterion. Okay, it only makes sense. Okay, we need to assess somehow this error, and this is very well done in terms of energies. Okay, and we have a very powerful result, and this is the only method in dynamical system where we have such a theoretical result. Mind you that in other techniques which we are going to learn and study about, this is not the case any longer. Okay. So this is a crucial result you need to understand. This will be extended to several variants of this discussion. Okay. So the balanced truncation procedure is the following error bound of the output of interest. Consider sigma I, the distinct Hankel singular values, okay? These are the values that we keep. Sorry. This is the dynamics that we keep, and this is the dynamics that we truncate. Then, this is very interesting. Then, this is the energy, the energy of the error signal is bounded, has an upper bound of twice this value, with respect to the input effort, okay? But this cannot be used in this form. It's used in a different form. The above result can be written in terms of the H infinity norm of the error system as follows. So this is equivalent to saying that the infinity norm of the error system this time is bounded by twice the sum of the truncated Hankel singular values. This is twice the sum of the truncated Hankel singular values. This is a great result. This is a wonderful result. Okay? So once you perform balanced truncation, you can theoretically determine the error of the approximation. There is no other existing method capable of doing this. This is the only one. Okay, so that's why balanced truncation is so important in modular reduction, and even if it's not very popular any longer due to the sizes of the original models, which are of billion order, and this cannot be applied because of the computation of the balancing transformation, this method is not liable and is not eligible to be applied for large-scale systems. However, the theoretical result of the error bound is crucial and well, is crucial and unique. There has been no other result of this form for any other of the methods people use now in model order reduction or in approximations of any kind. Maybe Padé approximations and these things can still have specific errors, but this is not possible. We'll see how the other methods cope with this problem. They are trying to solve optimization problems, which is not the case here. Okay, you don't need to solve anything. This is just a mathematical proof, and you'll see it in the book of Antulas. We're going to look at it. It's essentially proven inductively. So you truncate from n to n minus 1, and you see that the error is twice the Hankel singular value of order n, and then you apply this result inductively up to order k, or down to order k, okay? So this is a crucial result you need to remember, okay? You see, you have a proof here. So the proof has, exactly what I told you. The proof has 3 steps. First of all, you construct the error system. You construct the error system. This is the error system, okay? And then you show, not show, but show that if all the truncated singular values are equal to sigma, then, okay, then the infinity norm of the error is twice sigma, okay? And you use this result then to go to the lower indices, okay, inductively, okay? So this is essentially, and you can see, we'll see a detail of the proof in the book of Antulas, okay? All right, another crucial result, this is also something that is unique to balanced truncation, okay, is unique to balanced truncation because the other methods, as you'll see, are not capable of doing this, is the preservation of the stability. So if you truncate, if you do balanced truncation on a stable, original large-scale model, you end up with a stable approximation. And this is outstanding, if you ask me, okay? Also theoretically, once again, so these are theorems. These are not just conjectures. We think it's going to happen and things go crazy. No, it's never possible to do that because you have theoretically results vouching for the argument, vouching for the or sustaining the arguments related to this method. Okay. So if you consider the approximation AR, BR, CR given by the blocks A11, B1, C1, the blocks from the partition we have just performed, okay? Then A11, this is A11, has no eigenvalues in the open right half plane, and the systems A11, B1, C1, A22, B2, C2, so both the approximation and the truncated part have no Hankel singular values in common, okay? And AR has no eigenvalues on the imaginary axis. So stability and the Hankel singular values of the original system, they are also preserved. And this is, again, crucial. So this method is very thorough, okay? It's very sound from a theoretical point of view. This is a sound method. The problem is that it's always the case. You need a trade-off between the soundness of the method and the computational effort. As we'll see, the computational effort is very, very high, I'm afraid. That's why it's no longer so popular. There are people such as Peter Benner, who has the website called modelreduction.com, which I invite you to visit, and I told you about it before. Peter Benner has been struggling for years to show that this is not true, that this balanced truncation can have variants which are very efficient from a numerical viewpoint. However, this is not the case nowadays when people like to use other methods to perform model order reduction, and they are not interested in this very sound theoretical results any longer. Okay. But we'll go through all of this so you can get a flavor of what's going on. Okay? All right? So now we are talking about the computational complexity of such a method. Okay? This is very relevant. What's the computational complexity? Well, numerical stability issues. So the construction of the balance string transformation is usually ill-advised, okay, or ill-posed. This is an ill-posed problem. Why? Because you need inversions of these matrices, for instance, and this is not, you know that the inversion of a matrix is not good. Okay, we all know that in numerical methods you usually avoid matrix inversions. Okay, however, there are improvements. Okay, it's better advised to use the following procedure. You start from the Kalecki decomposition of both Gramians. You see here, both the controllability and observability Gramians are factorized. Then you compute the singular value decomposition of this matrix, not the eigenvalue decomposition, but the singular value decomposition of the factors U star Z, because this is easy to compute, much easier to compute. And then you construct T-balanced and T-balanced inverse, where there is no inversion involved. So this is more efficient, okay? But still it's not enough. This is still not enough. And I'll explain in a minute why. What's the computational complexity? This is the main question when you have an algorithm of this sort. BT leads to reduced order models with quality and stability guarantees, as I've stressed before. Okay, so this is highly relevant. However, the computation of the Gramians is expensive. This is where I wanted to go, because solving Lyapunov equations is very, very expensive. It's not only matrix vector multiplications, but it's an O to the power, it's a cubic. Okay, this is a cubic effort. This is a cubic effort, ON to the cube, which is devastating from a numerical point of view. So you cannot compute anything, and you'll do this exercise with a CD player, which is highly dimensional. And you can also try to if you have powerful MATLABs and powerful computers, you can easily generate matrices of tens of thousands and then try to apply and solve the Lyapunov equations. And you'll see, as I showed you before, that the Lyapunov equations can no longer be solved properly. I showed you this before. I think last time I showed you this on the computer. If you want to do Lyap or Lyap call, okay, of large dimension matrices, things are failing, okay, from a numerical point of view. For this reason, they say the balanced truncation is generally impractical for large sizes of the system. 10 to the power 5. No, I disagree. Even worse than that. No, I would say 10 to the power 3 here only. They are not popular for very large systems. And you'll see that even in your CD player example, okay? When you play with this method, you'll see there are severe drawbacks and limitations due to this disastrous numerical complexity, okay? Okay, proper orthogonal decomposition, we haven't studied this. This is another model reduction method based on snapshots of the states. This is a practical method, okay? So you construct a basis from the snapshots of the states used in this form, okay? And then you do the eigenvalues of such a matrix, and you build basis functions or the eigenvectors, okay? Then you minimize cost, a specific cost, okay? And then you build your reduced order model on this basis, projecting your system on this specific basis, okay? And then you compare the responses. So the response of a linear time invariant system to a single impulse with zero initial condition is this one. And then the reachability Gramian is given exactly by this case. So there is a relation with balanced truncation, because this snapshot matrix is actually used in this energetic form, WW transposed, Okay, note that W and W transpose, W transpose, this is a rank 1 matrix because W is like this and W transpose is like this. And when you multiply this is a rank 1 matrix. Okay. So unlike the balanced truncation, the POD, proper orthogonal decomposition, this is what POD stands for, does not take into account the observability gradient. So it's only based on one gradient. So from this point of view, this can be relevant because you get away with solving only one problem. Okay, only one problem. So another simplification, okay, is, for instance, for single input, single output systems. Okay, so you have GS, which is defined on C with values. So this is a number valid matrix. And then you have this G transpose S is GS. That means that the system is symmetric. We call it. Okay, so that means that there is a coordinate transformation such that T inverse AT is A transposed. Okay, and T inverse B is C transposed, and CT is B transposed. So this is a symmetric system. This is a symmetric system. In this case, okay, the controllability and the observability gradient, they are also symmetric to one another. And then it's relevant to only compute balance truncation for one gradient instead of two. For one gradient instead of two. So the case of symmetric system also simplifies the balance truncation procedure. Okay. All right, and then you have an example here. It's exactly your example from the assignments. It's the CD player example. Okay. So the goal of this model is to model the position of the lens controlled by a swing arm. Okay, that's the needle writing on a surface, or this lens thing. Okay, this is a 2x2 system. Okay, so this is not single input, single output. However, we study in the assignments a single input, single output version of this guy. Okay. Border plots associated with the HDM-based solution. What's HDM? I don't know. The dimension of such a system is 120. Okay. These are the results. Okay. Now, you perform, and this is what you're going to do in your assignments. You perform balance truncation on this example, okay? And then you see for several dimensions, be it dimension 5, dimension 10, 20, 30, 40, okay? You see the results. Look, for specific inputs, from input 1 to output 1. So this is input 1, this is output 1, okay? You see that at low frequency, the response is matched for all the dimensions. The response is matched for all the dimensions, okay? The same holds for the 2. This is input. No, this is input 2. This is input 2. And this is output 2. Okay, so you see at low frequencies, they match perfectly. Okay, the other channels have some issues, but this match perfectly. Okay, so that means that the steady states for some harmonic inputs with frequencies of up to this range, they match. They match in the steady state. So they also achieve some sort of moment matching. You see, as we tried to discuss it earlier. So this is a good approximation. Of course, the differences start to come at high frequencies. High frequencies mean transient response. Okay, so in the big difference between things is in the transients. Okay, that's where the issue is, in the transients. Okay. Okay. You can also use balanced proper orthogonal decomposition methods. So balanced PMS generates snapshots for the dual system in a, okay. So these are variants combined with a proper orthogonal decomposition. Okay, and you also have an application here. You have an application here of these guys. Okay. All right. Okay, and here you have the discussion. So what they haven't discussed here is what we tried to discuss before with the Hankel operator. And I think, as far as I remember correctly, so this is where the Hankel singular values come from. They are the first n singular values of the Hankel operator, okay? That's why they're so relevant, because the Hankel operator is the one mapping past inputs to future outputs, okay? All right. All right, so the Hankel norm, we also can define a Hankel norm of the system, and we'll see that there is a variant called Hankel norm optimization model reduction. This Hankel norm is the supremum of the output of the Hankel operator versus the input effort. Okay, and the Hankel norm is sigma 1, the sigma 1, okay, sigma 1, which is related, as we have seen, related to the infinity norm of the error, We have seen that. So the Hankel norm is relevant, and we're going to discuss a variant of things using the Hankel norm. Okay. So essentially, this is the balanced truncation procedure. Okay, this is the balanced truncation procedure. And now we are going to look in the book of Antulas. Okay, we're going to look in the book of Antulas, right? In the book of Antulas, there's a whole chapter dedicated to balanced truncation. Okay, chapter 7 is dedicated. Okay, so we are going to read a few details from the book so we can get a clear view. We can have a clear view of the things. Okay, let's have a short break, and then we'll meet again at 6 o'clock. Okay.
Okay.
Okay. See you then. I'm back. Let's carry on. Okay. You still here?
Yeah, I'm here.
Okay, thank you.
Yes.
So, balancing or balanced represent. We are interested in the balanced representation of a system. It's explained here. Roughly speaking, the states in such a representation are such that the degree of reachability or controllability and observability of each state are the same. Okay, I mean they are necessarily the same. However, they are represented by the same property, by the same quantity. That's the Hankel singular values. Okay, and it's explained here how the approximation goes. Okay, and what are the criteria, okay, for an approximation to be good. Okay, it's very nicely explained. I really invite you to read this part very carefully. Okay, and here there is a description of the things. There is a short technical description. Okay, it starts from the impulse response. So this, everyone in general in dynamical system has a point of view. Some people start from the time domain, some people start from the frequency domain. It's irrelevant because they're essentially they're all equivalent representation. However, each point of view serves a specific purpose of understanding. Okay, so here, for instance, Antula starts from the impulse response. We studied that in the first chapters of this course. Okay, all right. Okay, it's explained here how you how the approximation goes, and there is also a discussion about the Gramians. Okay, there is a discussion about the Gramians. R from reachability, O from observability. Okay, and it's explained where they come from, and then the balancing property is explained. Okay, and you recognize, we have seen this before. Okay, that the transformation given or yielded for the balancing is the solution of a specific optimization problem. Okay, so everything is very nicely explained, and then the concepts are presented. So first of all you have the concept of balancing, where you have to get P equal to Q. Okay, and there is an example. Look at this example: a 2x2 system with a reachability Gramian P and the observability Gramian Q. We use W and M, but that's irrelevant. You may use whatever notation is serving you. Okay. And how are P and Q obtained? Of course, they are obtained solving the Lyapunov equations. Okay, the Lyapunov equations. Okay, so AP, yeah, AP plus P A transposed plus B transposed equals 0, and A transposed Q plus QA plus C transpose C equals 0. These are the two Lyapunov equations to be solved. And then you have P and Q. Look at them. P and Q. Okay. And then you see the eigenvalues of P and Q and their corresponding transformation given by the eigenvectors. Okay. So this is the eigenvector of the first eigenvalue, and this is the eigenvector of the second eigenvalue. Okay, you know that for diagonalization, usually the change of coordinates that brings the matrix into a diagonal form is given by the eigenvectors of the matrix. Okay, it's very interesting here. So to find how difficult to observe the states and to reach the states it is, you can compute this specific product. You can compute this specific product. Okay, note that this product, as you can see, the eigenvalues of this product, can you see? Yeah, so the eigenvalues of this product, lambda 1 and 2, they are alpha, okay, plus minus J beta. Okay, this is a rotation matrix. This is a rotation matrix written in this form, where you have the real part of the eigenvalues on the main diagonal and the imaginary part on the skew diagonal. Okay, so this means that the eigenvector of P that corresponds to the smallest eigenvalue, so the most difficult state to reach, okay, most difficult state to reach, gives the almost maximum observation energy. Conversely, so it's explained here, okay, they explain the things we have been discussing about minimum input effort and output energy, okay. The question we are answering is, it says, given a continuous or discrete, this is also applicable to discrete time systems. Given such a system sigma, is there a basis in the state space such that the state difficult to reach are also difficult to observe? Very good question to start with. So is there a space or a basis where we can separate the highly minimal states from the almost non-minimal states? This is the question, okay? And the answer is positive. Yes, it is. And that transformation is called the balancing transformation, okay, such that this is transformed specifically into P equal to Q equal to sigma. And here you have the definition. Here you have the definition, okay? All right. Very nice remarks. It says, from a linear algebraic point of view, the concept of balancing consists of the simultaneous diagonalization of two positive semi-definite matrices, okay? And here you recognize how the balancing transformation is built, relation 7.2, okay? With this minus here, very important, okay? And these inversions. And this is the classic balancing algorithm, okay, with a Cholesky factorization, starting with a Cholesky factorization of the controllability gradient, okay? And here the Hankel singular values are explained, okay, and okay, this is also very interesting. This is a very important result because the whole balancing procedure is working due to this particular property, which is not always possible, and you can find examples when this is not true. So balanced systems have the property that if in continuous time the energy of the transition matrix e to the power at is less than 1, okay? In discrete time, this is this relates to the 2 norm of the matrix A. Less than or equal to 1 is strict inequality. So this is less than 1 if the Hankel singular values are distinct, and they usually are. Okay, and here you have a continuation of the example explaining to you how these things work. And you also have a variational interpretation of the things. Okay, so this is very interesting. You have given, since trace of the product PQ is the same as trace of sigma squared, this is in balanced form. Okay, then trace of P plus Q is twice the size of the trace of sigma. Okay, so the lower bound is attained in balanced case, P equal Q equal sigma. Oh, so here trace of PQ is trace sigma squared. Why is that? Because the eigenvalues of PQ are not changed with the coordinate, they're invariant to coordinate transformations. Okay, so the idea is like this. This is the product PQ. This is the product PQ. And then you want to end up with P equal to Q equal to sigma. But this is already from the very beginning true, okay? Because the eigenvalues are not modified, or they are not perturbed, they are not affected, they are not disturbed by a coordinate transformation. So these are very interesting relations, and here there is a proof of them, okay? And then there is the model reduction part presented here. The model reduction part. And it's explained, okay? And here is the error. Here is the error, okay? Here is the error bound, okay? Here is the error bound, okay? There's also a version for discrete systems, which is essentially pretty much the same thing, okay? This is the same thing, okay? So this result you need to study, and then this result, okay, compared to the discussion we had before. Okay. Oh, sorry. Okay. And there is also proofs, if you can have a look. So there is proof, the proofs of the theorems, which I'm not going to get into. If you want to look at them, fine. So there is a proof for and there's also a proof for the H infinity error bound. Okay, there is a proof of that. Okay, with some lemmas which can be used. All right. So there is a lot of interesting details you can have a look at if you're interested. Okay. There's also a discussion which you haven't made. It's a discussion about the H2 norm of the error system. So we have the infinity norm of the error system, and we can also have the H2 norm of the error system. Okay. So all right. And you can do that using a specific Sylvester equation, which you have to look up. Okay, but this is interesting. For instance, look, the H2 error of the H2 error of the errors, the H2 norm of the error system is given by this interesting trace. Okay. So there's a lot of interesting results you can see here. Okay. I'm not going to get into the details because I want to show you something else. Okay, and then there is a discussion about the numerical algorithms, and there is a lot of issues here you need to take into account. Okay, so you need to balance the entire system sigma, followed by truncation. Okay, so this is numerically inefficient. Okay, you can first do the Koleski factorization or decomposition of the Gramians. Okay, so this is one way to do it. All right. There is also other ways to do the things. You can do QR factorizations based on QR factorizations. Okay. All right. So it's and here there is a nice summary about all the algorithms you can use for balanced truncation. Okay, using Koleski factorization, using singular value decomposition, using this and that. Okay. All right, and here is an example. You can also use, this is an example performed on a Butterworth filter. Okay, because which vary with an order varying from 1 to 30. Okay, and these are plots. These are plots of the Hankel singular values. Okay, and of the balancing transformation, and then you can use approximations of these Butterworth filters. Okay, you can also have a canonical form given by the balanced form. The balanced form yields a canonical form, just like the controller canonical form, the observer canonical form, the diagonal canonical form. We add to that the balanced canonical form. Okay, we add the balanced canonical form, and it looks a bit weird. This is for single input, single output systems, but you can write it like this. And you can use it whenever the purpose suits you. Okay, It needs to serve a purpose. You can write a general canonical form and so on and so forth. Okay, and there is an example of a finite impulse response filter here. Okay. All right. So there is a lot of interesting things. Then you can also have other types of balancing, and this is where I wanted to get to. So until now, we have been discussing only the possibility of performing model order reduction for stable systems. But this is not necessarily the case, because you might run into non-stable systems, you might run into passive systems, you might run into all sorts of systems with all sorts of properties. Okay. Hence, you have to design balance, or the question is, can we design balanced truncation algorithms in order to preserve these specific properties for unstable, for dissipative, and so on? And the answer is yes. There is a lot of variants. There's many a variant of balanced truncation algorithms suitable for different classes of systems. Okay, and here you can see in general balancing. Okay, so what balancing in general means the simultaneous diagonalization of two gramians. But the gramians are with respect to the controllability function and the observability function. Why not substitute these functions to other types of energy functions? This is the question. So you can cook up specific energy functions depending on the class of systems you try to perform model reduction on, okay? And then you can do balanced truncation algorithms based on this specific energy functions. And here is a table, very nicely. Let me just stop for a while and emphasize that this book of Antulas is like a Bible, especially to our friend from the economics. If you want to study linear dynamical systems, use this book. This is like a Bible. This is a very good book. If you understand this book, essentially you have a good background in systems theory and linear systems theory for both modeling and control. It's not based on control, so you do not learn control here, but you learn a lot of modeling stuff. So this could be highly relevant to you. Okay, so try to read this book of Antulas. This is very interesting, very useful. So we have several types of balancing: Lyapunov, stochastic balancing, so you can apply this to stochastic systems. Okay, bounded real and positive real. Bounded real and positive real, these are specific properties with respect to the energetic behavior of a system. Positive real is equivalent to a passive system. Passive comes from passive device, such as a resistor. The resistor is a passive device. You can have this type of passivity property extended to dynamical systems. This is a notion stemming from mechanical systems. Okay, that the internal energy is not increasing, but decreasing to zero or to a constant level. Take, for instance, a swinging pendulum, a swinging gravitational pendulum, whose energy due to friction is going to decrease until the pendulum stops in the full downright position. Okay, so this is called passivity. Yeah, the pendulum is passive because no matter how I stimulate the pendulum, due to friction and the evolution, okay, the energy of the pendulum, of the free pendulum, after turning off the input that supplies energy, okay, this pendulum, the internal energy of this pendulum is going to decrease down to a, say, constant level, which is not the case for the swinging pendulum, but to zero. This also induces the notion of stability as well. Bounded real is a similar property of the same sort. Okay. Okay. So you see that each of the balanced truncation variants is related to a specific pair of Lyapunov equations. Okay. And the notion of error bound can be easily extended to all the variants of balanced truncation. Lyapunov balancing is the classic, the one that we have discussed so far, okay, with the controllability function, the observability function. and the associated gramians. We have discussed that. It's all clear. Stochastic balancing. Okay, you have a system A, B, C, D, which is square, so the number of inputs is equal to the number of outputs, is stable. Okay. Okay. All right. D is non-singular. This is important. So for some variants of the balanced truncation, the non-singularity of D is quite relevant. Okay. And since we're talking about stochastic stuff, we need a power spectrum. Okay. For this, and this power spectrum is given by this transfer function. So essentially, you have to reduce this transfer function, not h, but phi. Okay, not h, but phi. And look that you can write it in several ways possible, with a w and with a z. Okay, and now you have the controllability and the observability gramian, okay, of the system sigma. All right, with this b, this specific b, okay, you define the specific b, and then you consider this Riccati equation this time. This Riccati equation. So you have a Lyapunov and the Riccati equation, okay, and you do balancing, okay. So you have sigma w and sigma z. So these are peculiar cases of systems that can be balanced in a different form than the one we've been used to so far. Okay. Okay. So essentially, for these specific cases, such as unstable, stochastic, and so on and so forth, you build extended or auxiliary systems. If you build these, then you do classic balanced truncation on these auxiliary systems. Okay. So you turn your system to which classic balanced truncation cannot be applied into a system, auxiliary, augmented, or extended system, okay, where the balanced truncation algorithm is suitable, but the extended system has a different form. Look at this one. This one here has a different C function, okay, has a different C output, okay. And here it's also worth mentioning that you can have a specific relative. This is a relative approximation norm, okay, and it's related to the truncated. It's the same idea, okay. So the idea is the same. Is related to the truncated Hankel singular values, okay. The new Hankel singular values also look different, okay. And we have multiplicative error bound. We have all sorts of things here, okay. And then you have other cases, for instance, minimum phase and so on and so forth. I'm not going to get very much into details. I'm going to go to bounded real balancing. Okay. So an asymptotically stable system sigma is called bounded real if the H infinity norm is less than 1. Okay. That is, the transfer function satisfies this condition. So a system is called bounded real if the transfer function satisfies this specific condition for all frequencies, for all the real frequencies possible. Okay. And you also have the notion of strictly bounded when the inequality is strict. Okay. You can also find bounded real system discussed explicitly. Okay. Okay. These positive real and bounded real properties are related to some specific Riccati equations. Okay. They are related to specific Riccati equations such as 730 here, which is quite difficult. Okay. And the solutions here of these equations, they also satisfy this boundedness condition. So any solution between y min and y max, positive definite matrix, is a solution of this 7.30 equation. So how are you going to do balancing? probably we are going to use as gradients the y mean and the y max. Okay, because the y mean is the unique solution of 730 such that this matrix is asymptotically stable. So you can realize that the extended system has this specific form. The extended system has this specific form. Okay. Furthermore, bounded realness is also equivalent to the existence of a solution of another Riccati equation. Okay. And there is also a range of solutions z mean up to z maximum. Okay. Okay. And note that 730 and 731, they are dual to one another due to this property. Okay. So y mean is the z max, y mean of 730 is the z max of 731. Z minimal of 731 is the y max of 730, and so on and so forth. Okay. So what does actually balancing mean? So essentially you balance the minimal and the maximal gradients specific to equations 730 and 731. And this is what you do here, and you get a bunch of singular values. They are not, you cannot call them Hankel singular values any longer. Okay. Note that z mean, y mean, z max, and y max denote specific dissipation energy functions. We don't write them explicitly here. I have a paper on that, which you can study for the exam. It's my paper published in 2010, where you can understand these things, but that's for nonlinear systems. Okay, it's an extension. Okay, so okay, these are so these quantities here, they are called the bounded real singular values of the system sigma. Okay. And of course, based on these bounded real Hankel singular values, you can do truncation. And furthermore, you can also compute an error bound, an approximation error bound. Okay. We also have positive real balancing. What's a positive real system? So we had bounded real systems. Now we have positive real systems. An important class of systems is those whose transfer function is positive real, or these are passive systems. Okay. And there are sections where these things have been discussed. Essentially, positive real means that h j omega plus h star j omega is positive for all omega. This is positive real. Okay. Because these are also real quantities, that's why it's called positive real. Okay. We have also two Riccati, the positive real Riccati equation. You see? So we don't have Lyapunov equations like in the classic balanced truncation, but we have Riccati equations. It's the same like with bounded real. This Riccati equation has a minimal and a maximal solution, and they constitute, okay, or they create the gradients to be balanced. Okay. They also determine the energy functions. For instance, the minimal gradient is the minimal required effort at the ports to steer a state, and the output, the required supply, okay, is the maximum of this guy. Available storage and required supply. Okay, these are notions related to the property of passivity. And you also do balanced, and you have positive real Hankel singular values, and you can also have an interesting error bound. But note that in order to have positive real boundedness, you need D to be non-zero, and this is a drawback. Because in general, we don't have systems with ABCD. We have systems with ABC. In general, D is 0. So this is a property working very nicely for systems with D non-zero. The results can be extended, but it's not very trivial. It can be extended to the D equal to 0 case. Okay? All right. Okay. So this is another type of balancing and error bounds. Okay. There is also a modified version of these things. Okay. We can also have another type of balancing called frequency weighted balancing. These weightings, so weightings are additional systems are added to your system to emphasize specific properties, okay? So you want to approximate sigma over all frequencies, not only low frequency. For this, you need to introduce weighting, okay? So in many cases, a good approximation, it says here, is required only in a specific frequency range, okay? This leads to frequency-weighted balance truncation. You can have an input weighting and an output weighting, okay? A weight, you know what weight is, okay? Do you know what a weight function is? Do you know? You know what weight means? Hmm? I'm asking you.
Something like giving more or less important to
No, but how do you translate weight into Romanian?
pondere.
Exactly. Good. So now you have the weighted error, which is this one. Okay? The weighted error, which is this one. All right? And there are several methods, they say here. Okay, you can see here Varga, this was a Romanian guy. I think he used to be in Germany. Okay, and you can have gradients for the weighted system. The weighted system is the series input weight times system and output weight. Okay, and you can have new gradients. You can define new gradients. Okay, look here, and you can balance these gradients, and you can use specific Lyapunov equations for these gradients. Okay, and then you can perform balance truncation with this very weird error norm, but you can still get this specific error norm. And you have several methods, okay? Self-weighted and so on and so forth. You have all variants possible here. The method of Varga and Anderson, okay? You can also do frequency-weighted balance truncation without weights. This is even more interesting, okay? You can do this as well. Okay. You can also do balance truncation using time-limited gradients, just like the one we started with when we discussed about controllability and observability. Okay. You can also do closed-loop gradients and model reduction. Essentially, you can do model reduction of a control loop, which is very interesting. Okay. You don't have to do this only in open loop, so for the classic system H of S, but also for the system with the controller. This also means that you can do model reduction of controllers. Okay, so closed loop balance truncation. And also you can do balancing for unstable systems. You can use time-limited gradients for that. Okay, and there is an illustration of the method here. Okay, and you can use also the infinite time gradients. Okay, to do model reduction for for the answer for unstable systems. Okay, and then you have a summary, and that's it. Okay, so this is in a summary the whole idea about this notion of or this method of the balanced truncation and balancing. Okay. Okay. Right. Let's see now. Let's stop the screen for a minute and see if we can have something interesting to show in MATLAB. Okay. Let's see the commands for model reduction in MATLAB. Let me share this screen. Okay. Can you see the MATLAB? Okay, you can. Yes, you can. So we have this example. Okay, let's run it. Okay, so we have this. This is the minimal realization. Okay, AMBMCM. So this is going to be reduced because we have to start with the minimal stable system. The system, oh, it's not stable, I'm afraid. The system is not stable. So we have to be careful. Have to be careful about this. Let's see. Yeah, it's not stable because here we use minus instead of a plus. Let's see how this goes because I need a stable system. Ooh. Oh no, this is not stable, I'm afraid. 0.0. Trying to make it stable. We cannot do that. Oh, I think I can, but this is a mistake here. I think it's stable now. Okay. Let's see. AIG min_sys.a. It's not stable. Why is it not stable? Oh, should be minus everywhere, because otherwise this is not right. This is stable now, you see? We have a stable minimal system. So min sys is the minimal system. And we're going to do approximation of this min sys. Okay, let's just comment on this, because we don't need this part. Okay. Okay, let's make it here CLC. Okay, so we have the minimal system, which is this one. All right. Okay, and this is okay, that's nice. And we have it in a diagonal form, so we can use diaxis or min sys. And we need to reduce this. Okay, let's see what types of commands we have with balancing. So ball red, I remember it's one of the commands. You see, ball red, and here you need to put an order. Orders. Okay. It's using implicit balance techniques. Okay. Okay. So orders. Let's see here orders. So we do here balanced truncation of the min sys. Okay. And here we have orders 1 through 2, because okay, you have balanced truncation order 1 and order 2. Number of states. 1 or 2 states is a vector of integers. Okay, is a vector of integers. Fine. Oh no, not here. This has to go at the end of this file. And now let's see, RSys, just like they call it, is ball red of min sys and orders. Let's see if this works. You see, it gave you the balanced truncation models of order 1 and order 2. You see? So this one here is the first order approximation, and this is the second order approximation. This is the second order approximation, okay? Okay, let's plot them. Okay, let's see. To have a full view of the response, we just look at the frequency response, at the Bode plots, okay? At the frequency response. So we just use Bodemag, min sys, and RSys. This is not good. Let's see if you can do it, because we have 2 systems. So Bode is the command showing frequency response of systems. Okay, the Bode plots. Oh yeah, you have all of them. All of them. You see? So from input 1, because B has 3 inputs. This is for input 1, 2, and 3 to output 1. You see? Look, the red and the blue are the same. This blue one is the second order. Okay, it's the last one. So you see in the low frequency area, the second and the third one, so the second order approximation and the original third order model are the same. They are the same, you see? Look, it's also the same with the first order approximation, which is ridiculously looking. This is the first order approximation, you see? So this is very interesting, okay? This is very interesting. Now let's look at the errors. Let's look at the errors. I'm not sure what the command is for the error. Help ball trunk. Let's see if ball trunk still exists. No, it's not. Help. I need to compute the error. Mod red. Okay, so this is another command. You see? This is another command, but first of all, you need to compute your balance truncation yourself. If ball red is doing it automatically, for mod red you first need to compute the balance truncation of this. Okay. I'm not seeing the error. Okay, but the error is easy to compute. Okay, because you can have a look here in RSys. You can have a look, or essentially you can have a look at the Hankel singular values, okay, of the original system, okay, Hankel singular values of the original system. All right. So let's see what the Hankel singular values are. Help Hankel. Yeah. Hankel square matrix, tuplets. Now this is about Hankel matrices. Okay. It's not very difficult because you can compute. For min sys, we need to compute the controllability Gramian, the observability Gramian. Okay, so here we have R M equals CTRB min sys. Okay. So these are the minimal ones. These are to be reduced. OBSV min sys Hankel singular values HSV equals eigenvalues EIG of RM times. Oh, but these these are no. Sorry. I made a mistake. No, I need the Gramians. Sorry. Not the controllability and observability. I need the Gramians. So W is up, and I'm going to use call with using Koleski factors of min sys dot A and min sys dot B times min sys dot B transposed, and the observability Gramian M. This is Liap Koleski min sys dot A transposed min sys dot C transposed times min sys dot C. And now I have W and M. And the Hankel singular values are the eigenvalues of the product W and M. Okay? These are the Hankel singular values. Let's check it out and see where they are. Look, these are the Hankel singular values. You see, it's 2 2 and 1. You see, that's why the second order approximation is much better than the first order, because the Hankel singular value decay happens between the second one and the third one, but not between the first one and the second one. So it's not good to truncate and keep only this. It's good to truncate and keep both of this. And then the approximation error is very small, because the approximation error bound in the infinity norm is given by the sum of the truncated, thrown away, neglected Hankel singular values. So if you have a second order approximation, the error is 1.24. Whereas if you have a first order system, the approximation is coarse, okay? And the approximation error is given by the sum of these two numbers, okay? So this is essentially the idea. So it's good. This approximation is the good one. This is a lousy one, okay? All right. Do you have a little bit of understanding? In the next assignment, you'll have to play with these methods for the CD player, or not the next assignment, in a future assignment, okay? Because we are a little bit behind with the assignments. You'll have to play with these for the CD player and for the building example, okay? And you have to find an efficient way to have it computed properly, okay? Just watch out and take a close look at the MATLAB commands you can use to make it numerically efficient, okay? This is a MIMO system, so it looks, this balanced truncation works very well for these MIMO systems, okay? Any questions, please? Any questions, please? Questions, remarks? Questions, please? Please try to do your assignments. Okay, there is assignment 4 waiting for you. Let me try to show it to you. Assignment 4 is here. Okay, with minimal realizations. Okay, here you have assignment 4. Please do it. Okay. Yeah.
Okay.
I'm listening. Okay, fine. If there's nothing else, we can call it a day.
I have a question.
Yes, please.
Can you repeat the explanation about Henkel singular values?
Yes, what about them?
So we have 3 values, and
You mean in this
so
MATLAB example?
yeah.
Sure. The dimension of the original system to be reduced is 3. Okay? That's the dimension of the original system, 3. So you have 3 Hankel singular values. The Hankel singular values are the eigenvalues or the singular values of the Hankel operator, which maps past inputs to future outputs. The Hankel singular values are energetic measures. They measure simultaneously the minimal input effort to steer the state from minus infinity, so from 0 to a state x0, and also emphasizes the output influence of the state in the energetic influence of the output of the state in the output. Okay, so this Hankel singular values because it's small, it says that state number 3, whichever that might be. So in the state number 3 in your three-dimensional state space, the third state is almost non-minimal because you need a lot of effort to control it, and the output, the outcome at the output is very limited. So it's almost non-controllable and almost non-observable. So it can be neglected in the dynamics. Whereas these Hankel singular values, because they are large, that means that those states are easy to control and have a strong or a serious influence on the output and need to be taken into account. They need not be neglected. This is the significance. Okay? They are state space invariants because no matter how you transform your systems, their Hankel singular values are the same, irrespective of the change of coordinates you apply. What other explanation would you need?
This one clean me out.
Furthermore,
Yeah.
the Hankel singular values are relevant for the approximation error bound. You can see the results in the slides and in the book. Okay.
Okay, thank you for the explanation.
Okay.
Very helpful. Very helpful.
Fine. If you have any other questions, please. Fine. If there is no questions, then I can leave this call open for you. And you can call me, you can ask me questions, or you can write on the chat questions for later, okay? Please do not forget about the assignments, okay?
Okay, thank you.
Okay.
Thank you very much.
See you soon. Cheers. See you soon. Bye.
Bye-bye.
Bye. Mama? Pentru nimic, bă. Nu spitale, nu școli, nu dezinfectant. Da? Da ce înseamnă să citești? Ca să știi cât îi plătesc acestui stat nenorocit în fiecare zi. Pentru ce, mă? Pentru propi? Pentru Nicușor? Pentru Voiturescu? Pentru asta plătesc pe stat? Pentru Ciolacu? Deci nu-i cop. De asta ți-am spus să stai în stat care te implică să lucrezi. Da? Și la asta adaugă impozitul anual pe chirii, impozitul dat de tine. Deci sunt cuvinte, nu? Ai văzut de tot. Nu sunt cuvinte? Deci nu sunt cuvinte. Bine, poate să fie pierde cu condițiile, dar tot aia era. Înainte o fac o plătă direct politehnică, acum mi-a din salariu, deci după ce mi-i dă mie, facem la mână. Eu am ocupat de două. Nu mă ocup, că ai văzut. 42 nu mai contează, e peste 40 de. Nu crește și de mine. Deci eu 45%. 40-45% sunt taxele. Da, și asta înseamnă 40-45%. Nu știu ce dau la ANAF, nu știu. Da, păi și alea sunt impozitate în toate astea. Nu, da, cine contezi, dau, dar îi dau netul, nu-i dau brut. Dacă am, nu am, nu, acolo au fost ai mei toți. Dar poți să scazi orele de la plasa acolo. Mai, doar dacă iei cu japca sau cum îi faci? Și ce avem la felul 2? Dacă la felul 1 vrei să faci supă. Un pic.